running now. First I was interested whether you're already planning ahead for exams or not as much yet. We'll finish all our material this week, so we have another week of term next week. Many lectures also finish early and don't use that for new material, but it's still timetabled sessions that we can use. If most of you kind of push preparation until after the holidays, then maybe it's not the best use of time. We could instead improvise some sessions in the first week of January. Does someone know from the top of your head the day of our exam? Has that stayed what it was? Pardon? 18th. Yeah, okay, that's what I have in my calendar too. Okay, so that's confirmed. So we still have 2 or 3 weeks almost, but yeah, you have other exams. The first week of January after the break is still kind of free from exams, I think. So we could either have some Q&A sessions next week or push them until after Christmas. But we still have this week first, so I'll ask you that question again, I guess. Let's do the housekeeping. Scared of exams. Well, that's what preparation is for, to make you less scared. Also, let me remind you about the cheat sheet you're allowed to bring. 1 A4 page, but you can use both sides, but that has to be handwritten, but you can put as much as you feel is useful on it. Yeah, I guess we'll discuss some more exam questions tomorrow. Okay. There's always a trade-off whether you announce before starting a unit that it's not part of the exam or not. If you do, then the room might be a little less populated. On the other hand, I don't want you to just, well, I feel it's still better than making people come and then afterwards say, actually, it's not part of the exam. I hope you enjoy this part. I certainly like this unit a lot. You'll see whether you agree. And it nicely ties together what we've left open in the last unit. So welcome back to Efficient Algorithms, COMP526. The last time a new unit, Unit 9, our Christmas lecture, where we'll talk about range minimum queries. I'll tell you what this is in a second. Just to set the scene, it's a little more advanced towards the end than I was comfortable of putting on the exam, so it's just for your enjoyment or for your entertainment. But it also nicely closes one last black box that we left open in Unit 8. And since that was just last week, I hope you still have some fresh memories of that. I put some learning outcomes, but again, these are just for orientation. We'll look at this problem, abbreviated as RMQ, range minimum queries, and the connection it has to things we've discussed in the previous unit. We'll see some solutions for that, and up to this point, I think it would be fine to do it as part of this module. But in isolation, it doesn't add too much interesting opportunities to ask exam questions. And then we'll look at the more sophisticated ways that make the best possible solution of this problem possible. Okay. Let's start with a little bit of introduction and what this problem is about. So first of all, just the definition. What is the range minimum query problem? It will at first sound like a very simple and slightly strange problem. Why would you care about this? But we'll come back to that in a minute. So the input is just an array of numbers or arbitrary objects. Static here means it's not changing over time. That's to simplify the problem, and it will be interesting in that variant for us already. So you have n numbers, and you can pre-process that array of numbers up front, and you can build some data structures, do whatever you want. And then later I'll ask you queries, which will always be a contiguous range, so some start and end indices. And you have to tell me where's the minimum in that range. So in this case, if I ask for the range minimum query that starts at index 17, index 7, and ends at 15, that's the range. So if you look at those numbers, 2 is the minimum. So I return that position. Two nitpicks about this. I'm not asking for the value of the minimum. I'm asking for the position. So you're returning an index, not a number, a value here. So you would return 10. And if there's ties, then we take the leftmost of those occurrences. Somewhat arbitrary, but that's the conventional way to solve ties here. So far, so good? Let's see. So just a simple example query to test that we're all talking about the same problem. So what you should send back as an answer is just one number. Add 66 on the attendance code, so maybe we can get a few more here too. Let's wait until 40 and then, okay, there we are. Now here's the results. Again, what you can't see is 9 people are behind the 1. And well, a few other answers. Okay, so let me go through this. I want to draw this the same way. The range, first of all, that we're given, it starts at index 1 and ends with index 6. So the range we're looking at is this. That's the part of the array that we're focusing on, and only what's inside of this range matters. Now we're looking for the minimum, and the smallest number in that range is 4, which occurs twice, here and here. And the actual answer that we return is 1, because we're supposed to return the leftmost index of that minimum. And that's here. Okay? That's what this is about. Now you may wonder why that's at all relevant or even connected to what we've done last time. But we'll come to that. A few more comments on the definition. First of all, notice that everything is comparison based. I'm asking for a minimum, so all I need to be able to do is compare 2 elements, 2 objects, and tell which one is smaller. So I defined it in terms of numbers because we'll use it for that, and it's kind of without loss of generality. But really, it's comparison-based, so it could be arbitrary objects. And then we have, unlike in some other problems, we have two types of running times that we're simultaneously trying to keep in check. One is the pre-processing time. That's the time you spend on the array before any query comes, and then the time per query. And you can maybe imagine that there will be some trade-off between the two. So what we want to keep both in our solutions and be able to talk about both. So I'll use this angle bracket notation to say the two running times are such and such. And the first one is pre-processing, second one is query. Okay? So without really knowing or without thinking deeply about this, maybe you want to give me your best guess of what could be achievable. And I mean, if you've, sorry, no. If you look forward in the slides, of course, you can find the answer, but the goal would be to get your gut feeling instead. So your answer should be of this form with two running times. So for example, in angle brackets 1, 1 would be you spend constant time on the pre-processing and constant time on the queries. I mean, spoiler alert, that's not going to be possible. That's the kind of format that you're aiming for. Yeah, some good answers. Okay, let me show you. Most people seem done. Okay, you broke the algorithm for doing these wordles. Word clouds. I mean, the middle one, big O of n for both, might be what we could read it as. Well, I don't want to give much away. We'll see. Okay, I'll just leave it open. So that's the problem. Now let's put this a bit in context. And there were so many acronyms that I thought it's more fun to put them all in the title instead of the proper title for the section might have been Connection to Other Problems. In the next subsection, we'll see how the range minimum query problem, the first of these abbreviations, connects to some of the others that you might hopefully remember from Unit 8. We'll come back to those. And then that might give you more motivation for studying this more abstract problem. The range min query problem is just on these arrays of numbers. And you might ask, why would you want to know the minimum in a certain range? What's that good for? So remember from Unit 8, there were a few things that we did where the other abbreviations from the section title popped up in. The first thing was we were looking at suffix trees, these beasts. Just so that you remember, it's the compact trie of all suffixes of a text, right? And we were using these for different string algorithms or making different string problems fast. One of those was the longest common extensions problem, where we this was part of solving more interesting questions with suffix trees. We used this as a building block, and then longest common extensions could be reduced to finding lowest common ancestors in the suffix tree. We wrote that at the time like this. So if I want to know the longest common extension of two suffixes that start at position I and J, then I can look in the suffix tree for the two leaves that correspond to those two suffixes and find the earliest where their paths join if I move up, or the lowest common ancestor if I move down from the root. And the string depth of that node, that was our longest common extension, or the longest common prefix. And well, we've had this example of the leaves 5 and 7, but I think it's too small. So if you want to see the example again, maybe we go back to Unit 8 instead. So that's the connection between those three things. We had longest common extensions of two positions. How far can you read to the right in the text and see the same characters from I and J, which is the same as the longest common prefix of two suffixes. And we connected that to the lowest common ancestor of leaves in the suffix tree. The second bit that is borrowed from Unit 8 was this promise that we can do lowest common ancestors, LCA queries in trees in an efficient way, namely in our notation, theta n pre-processing time and order 1 query time, constant time for a query. Okay, so that was the promise back then, but I didn't tell you how to do it. Then there's one last thing that we studied back then. And that was along the journey of getting rid of the suffix tree for our problems. Instead, we used the suffix array. Then we found the suffix array is not good enough for some problems. We also need this LCP array, the longest common prefix array. And the longest common prefix array stores this longest common extension for two adjacent leaves. Right, remember we had this picture that we walk along the leaves of the suffix tree from left to right. Now, whenever there's a green connection between two leaves, they are adjacent in the order of the suffix tree. And then we have, or in alphabetic order. And for those two, we have the lowest common ancestor, we have the longest common prefix. So the string depth of the lowest common ancestor was 0 here. Between these two, it's string depth 1. Between these two, it's string depth 2, and so on. So the LCP array, as we defined it in Unit 8, already has some answers for LCE queries, but only if these two leaves are adjacent. So I could, for example, ask for LCE of 5 and 7 directly by finding the right LCP entry. But if I'm asking for two other leaves that are further apart, there's no entry in the LCP array that directly gives that answer. But you can translate between the two. And for that, let me zoom into this picture a bit. And let's find, again, 5 and 7. These are adjacent in sorted order. The suffixes aban and an, there's nothing in between. There's no suffix that's between the two in lexicographic order. That's why the LCP array has directly an entry that tells you the longest common prefix between those two. Same as what I've just said. But what if you ask this about an arbitrary collection of two, an arbitrary selection of two suffixes? For example, I could ask about 5 and 1. So these are two suffixes. They're not adjacent. So what's their longest common prefix? They span a certain range in the alphabetic order, and they span a certain range in the LCP array as well. And the thing is that we have to find the smallest entry in that range to get their overall longest common prefix. And the reason for that is if you look at the strings, these red strings, the things that they share, that adjacent suffixes share, kind of the lowest common denominator is what determines the longest common prefix between this one and this one. So all of those start with an A, which means from here to here, I have to have at least one thing that they share. From here to here, I have 2, which is more than 1. From here, we have even 3. But the smallest number will always dominate, because that means you have the same minimum number all the way through. That's the longest common prefix between those two. If there was a longer common prefix, then it should be shared among all those in between. That's by alphabetic order. If these two shared 2 letters, so the first 2 letters here were the same, then anything in between in sorted order also has to start with the same 2 letters. So we find that the longest common extension of 5 and 1 is the same as this range minimum query in the LCP array from, well, the positions here are numbered a bit awkwardly, remember, 1, 2, 3, 4, 5, and so on. So from position 2 to 4. And that connection is general. So if you want to express this in the general case, what you get if you have two starting indices of the suffixes, the starting index is not the position in this list, that's the number in here. So the first step, that's why that slide is here, is to translate from starting index to the position in the sorted list. That's the rank array. So we take I and j and convert them to their ranks on the right-hand side. We do that with both. Now these numbers, they might not be in sorted order. It might be that they swap relative positions by moving to the right. That's why we have to take the minimum here and the maximum here. And the +1 comes from this convention of the LCP array to sit between two suffixes, but then it starts with index 1. But overall, the connection is relatively direct. If you want the longest common extension of two suffixes, you need to find the range minimum query of some part in the LCP array. All right, so again, the connection is just translating the pictures from one side to the other. But if you have things in sorted order and they share a certain common prefix, then anything in between has to share at least that much. And also, if there was anything longer, then they would also share this. So it's an exact equality. So if we translate what that means for any solution for the range min query problem to longest common extensions, it means that we get essentially the same running time. If we have a PQ solution for range minimum queries, we can use that solution using the inverse suffix array to directly answer longest common extension queries. And we use the same pre-processing time plus I guess there should be a plus order n, because we need the time to compute the suffix array and the inverse suffix array. But the query time stays the same. And any interesting pre-processing time will also be at least linear. I think the cleaner way to express the same thing here is for longest common extensions, when we're already given the rank array and the LCP array. Yep. LCP. So if you remember what we wanted, the claim here was we can do it with linear preprocessing and constant query time. That would be the final goal for the range minimum query problem. And you can compare that to what your guess was, what might be possible. Okay. In the next section, we'll look at a few relatively simple solutions for this problem. They will not achieve the optimal preprocessing and query time yet, but there are building blocks that we'll use. And also, they're much easier to understand, so we'll start with those. First, a few trivial things you can do. Very easy. Showing the extremes of the scale. One option is you do nothing at pre-processing time, which means at query time, you have to do all the work. All the work means, well, we have to find the minimum in some range. So we just walk through and keep track of the current smallest element. If we do that, say, from right to left, we can keep track of the last occurrence. That's the leftmost. Different options. And then you need time proportional to the length of the range that you're looking at. But in the worst case, the range that you're looking at is the entire array. I can always query with 1 and n, or 0 and n minus 1. And then the query time for the worst case is linear. And that's not particularly useful. That's too slow, but it's an option, right? And we have no pre-processing time. I could basically have said 0, but order 1 is an upper bound is, of course, also true. The other extreme end is we do all the possible work at pre-processing time, and at query time, we just read off the stored result. How would that look like? I can store a 2D array m for minimum, which just stores in mij, it stores the answer to rmqij. And then the query is trivial. Query just says return rmqij, return mij. But the pre-processing is super slow now. If I do it really stupidly, I could say for I from 0 to n, and then for j from, I guess it can't start before I. Okay, we can have the same. now I have to compute the minimum. So we could say, let's spell this out, doesn't hurt. And then I probably want to remember the position rather. Is I. Then we do a loop for from I to j. And if my previous minimum is no longer the minimum, so if I compare it with AK, and AK is strictly smaller, then I update my entry A. That would be one easy solution. I have to store this. Okay, gets a bit running out of space here. That would be simple code to compute all the values mij up front. And this takes cubic time because I have one loop that takes n iterations, another loop that takes n iterations, and then a third loop in the middle that in the worst case takes length n. And you can again prove that asymptotically it's cubic. Can you do better? Can you somehow speed that code up a bit? You can massively speed it up in this inner loop because we're really throwing away all the knowledge from past rounds. If you iterate over the subproblems in a slightly smarter way, then how do you get from mij to mij plus 1, for example? So I make the range 1 bigger at the right end. Now, if that's my previous range, that's the new element, j plus 1. In the range from I to j, there's some minimum somewhere. Now, if I add one more element at the end, there's two options for the minimum of the new entire range. It could either be here, or it can be this element. But it cannot be any of the other elements, because these were already bigger than that element. So I can make the next bigger range and find its minimum in constant time by just comparing these two options. Right? So that's how we get the running time down to quadratic again, which is now the size of this array m. And we have to at least fill that. So there's no way around it. Maybe it's worth spelling out some code for that. So all we have to do is make sure we iterate over m by order of the length of the range. So we can have anything between 1 and n elements. Then we iterate over the range. It can start at 0, anywhere up to n minus l. And then I guess we can do a case distinction. If the range is just 1, then I'll store at I, mi, I plus l, I'll store I. That's the index of the minimum if I just have a single element. And otherwise, there's a smaller one. So I can take my I and I plus L minus 1. We'll use that a few times. Let me give that a name. So editing the code on the fly is maybe dangerous. So one option is this. The other option is j plus 1. I have two positions that I have to check, the position of the previous minimum and the new position that I'm adding into the range. And so, again, running out of space. Let's move it a bit up here. Okay, I can cheat a little bit. So I'm checking now if A of A is less or equal A of B. Then I keep A. And otherwise I use B. Okay. So with this code, we can solve all the pre-processing in quadratic time. So I have two loops. This one runs n times, this one runs n times, and everything I do inside of here is constant time. It's just a fixed number of instructions. Okay, but zooming out again, that gives us order n squared pre-processing time and then constant query time. So the constant query time is great, but we're wasting a lot of space. And because we have to fill the table, even if we're smart about computing the next minimum, we still have to write to the output. So we won't be able to improve upon this n squared running time for pre-processing unless we don't store as much data. Okay, how can we store less? The idea is to do what we've done in the trivial pre-processing everything step, but don't remember as much. Actually remember very, very few of the entries. And what works here is only remember entries where the range that we cover has a length that's a power of 2. Okay. First of all, immediately from that, we can bound the number of entries in that table, because the overall length of the range is never more than n, so there's never more than log n powers of 2 below n. And so we have for each starting point at most log n entries, which is much smaller than n squared. And it's convenient to store those. Instead of giving the start and end index, we just give the start index and then the power of 2 for the length. Then you have it back in a nice contiguous piece of memory. Now that's fine. Suppose we can compute those answers and store them. How is that helpful for queries? We can no longer just return m of I and j. I might not have stored the answer, right? Luckily, I can still reconstruct the answer. I cannot immediately output the answer, but I can reconstruct the answer in constant time. And the reason for that is as follows. No matter how long your actual query range is, in this case, it goes from 5 to 18. So I guess it's what, 14 elements? That's not a power of 2, right? So I don't have an entry in my table that directly tells me for this range where's the minimum. But what I always have is a value k that's, a value k, so that 2 to the k is between the length of my query and half of that. That always exists by definition. And so I can cover my red range by 2 ranges that have a power of 2 as length. And it's always so that they at least touch, or actually they always overlap by 1, because I could have made this strictly less. Okay, the ranges definitely at least touch. So they cover the entire red range. And so where's the minimum in the whole red range? Well, we don't know, but if there's a minimum in the blue range here and a minimum in the green range there, it has to be one of the two. If it was any other element, then there's a range where they are together with that element and the answer in that range contradicts, for example, I mean, the 10 is definitely not the minimum. I should have circled the real minima, which are marked by the arrows. Sorry, that was more confusing than helpful, maybe. Why can this element never be a minimum? Well, if it was, then it would have had to be the minimum also in the green range, but RMQ for the green range said, no, here's the minimum. So the overall RMQ in the range from I to j, from 5 to 18, is one of those two positions, whichever gives the smaller value. Again, with ties broken to the left as before. So I ask these two subqueries, which have a length of power of 2. So these are just stored. So, okay, I don't know if I can fit that here. That one's stored in M prime IK. And the green one's stored in M prime J minus 2 to the K plus 1. A bit less nice, but still it's just some number that you can compute. So these two elements you can look up. That's two indices in the array, maybe 10 and 17. And then you do this check. You find the values in A, do one comparison. So this notation argmin just means the position where the minimum is attained among those two options. So you would have code that's like this. If A of A is less than A of B, then the result is A, otherwise it's B. So that's how you get by with just n log n entries instead of n squared. The pre-processing can be done similarly to what we've done for the stupid version where you compute all answers. Because if you go from a range I up to I plus 2 to the k minus 1, and now you want to go to that with the next largest range, so the power of 2, one bigger. What does that look like? This is one range, and then you have another one of the same length, and that gives you that range. So you have the same situation as here. You have a blue part on the left, and you have a green part on the right. The minimum of the entire range has to be an element from somewhere in the range, so it's either the minimum of the blue part or the minimum of the green part. And both of these you have computed because they again have a power of 2 as length. So you can do with a similar trick. You look up the smaller ones, compare which is smaller, and that gives you the result for the long range. So as before, you can fill each entry in our table in constant time. So the overall pre-processing time is n log n for the size of the table. And query time is still constant. It's a different constant. It's slightly slower than before. We can't just look up one entry in an array. Instead, we have to look up 2 entries in an array and do one comparison. But still constant time. Okay, so far so good. That's about as far as you get with simple tricks like this. So you can try to think about how to make further improvements. But I'm not aware of a solution that gets there. If you're just trying to do that approach, somehow get rid of even more elements, it doesn't seem to work. So instead, you need some fundamental different approach to solving that problem. Shall we do a wee little break before we dive into the grand final of that unit? Almost. Nope. Good, let's give it the usual few minutes. There's a few very important questions to comment on. I mean, don't be too scared. Preparation is all. Many people have passed this before you. You will too. Obviously, you don't want to fail. Yeah, the most important question of all, of course, that's a tie. It's my Christmas tie. I would normally have come in a proper Christmas sweater. It's Christmas jumper day, apparently. But we had a photographer coming earlier to take some new pictures for our websites. And I felt they're maybe more useful if they're not with a Christmas jumper. Right, so just the tie today. And you've dug this out, it was the 18th of January. If it hasn't changed, it starts at 10 a.m., but you have some days to find out. It should show up in your exam timetable, which probably is on Liverpool Live. I never get to see the student-facing side of our IT, but there's some dedicated place where you can see your exam timetable, I've been promised. And it should show up there. If you check there and it doesn't show up, that would be concerning. So maybe then check with the student experience team. But yeah, 18th of January should be the day. If I make the exam easy, does that mean the marking scheme has to make up for it? And so we're, first of all, the exam is already done. I had to submit that many weeks ago. And of course, there's a balance there. The color of Christmas tree. Is that a question? It's green, mostly. Until you leave it for too long, then it's brown. Question bank in that sense, I mean, there's no database or something like this. What you can use is the past exam papers and the mock exam plus tutorial 10, which these are all old exam problems. So call that a bank if you want. Yeah, I can, and I actually did. So it's on CampusWire. Check that out. It will also come up on this all-student Canvas course soon. Okay, I can't be bothered to read all that stuff now. Maybe just put it on CampusWire again. And I can leave it here, but if there's time at the end, I'm happy to do it on. Well, we have 1 minute now. That might not be enough. Okay. one of the few things that doesn't work with this software. There's no command to center the picture in the viewport. That would be convenient. Well, okay. Well, let's move on. So what we've seen so far were the somewhat elementary approaches to this problem. And they got us to n log n pre-processing. But it seems we're stuck at n log n. Now, we've seen things like this before. There's a log n factor missing to optimal. We've seen this a few times in other contexts. And there was a trick to make certain blocks and then compress things so that you can reduce the input size from n to n divided log n. We've used that trick a few times. And in a way, that works here too. But that's not the end of the story. You still need to solve some remaining part. So we'll first do a little detour. In the next subsection, we'll look at Cartesian trees as a alternative look at the range minimum query problem that will ultimately help us to find a better solution than the n log n entries of a sparse table. But let me first just show what it is before we motivate it much from an algorithmic point of view. Now, let me point out here, to make the picture or make the picture analogy, the metaphor work well, here RMQ is the range maximum. You could have done it with minimum and then draw the picture the other way around. But we're computer scientists. Our trees have a single root and it's at the top. Let's stick with that very sensical notion. So imagine you have an array of numbers and you want to solve the range maximum query problem. So for every range, you want to know what the maximum in that range is. And to visualize it, let me draw a bar or pole instead of the numbers that has as height the value of that number. The overall maximum is then obvious from just visual inspection. It's this one, right? But if you want a range max, you can do the same. You constrain the array or the picture to a certain vertical slab. And then within that, it's the pole that sticks up the most. So as a human, it's obvious in the small example what the maximum would be and where it is. Okay, so as before, that's just the definition. And I'll point out again, for this picture, I'll flip the notion of min and max just to make it nicer to draw. Okay, here it is. For the overall task, we'll pre-process the answer to the array to get a faster answer. Now the Cartesian tree results as follows. You have a root node at the overall maximum. That's this position in our example. And then that basically splits the problem into two halves, maybe everything to the left and everything to the right. In this case, the to the right part is tiny, but in general, it's two parts. And then you compute recursively the same Cartesian tree on these two subproblems and make them, so there's some subproblem tree coming here. And okay, let's make this a bit nicer. There's some subproblem subtree coming from this, and you append those as the left and right child of this root node. Okay, again in nice. If I take everything to the left of that node, the next largest is this element. So that becomes the root of another Cartesian tree, a subtree, and it becomes the left child of the overall maximum. And similar on the right, well, there's just a single element, so it's just a single node, but it becomes the right child of the root. Now we further split up things. So there's the range between those two, and there's the range left of this guy. So in general, we will always have ranges that are from some previous node to some other, so between two poles. And on those we recurse. So here again, if I let this largest element between those two is this, so that becomes the next node. Largest element in this range is that one, so that becomes the next node. One more time. Largest element to the left of that node is that. Largest element between those two is this one. Between those two is this one. I guess you get the picture now. So you recursively refine the range, and always the maximum becomes the next node that you connect to what you've already constructed. Okay, awkward definition. Why do we do this? Okay, that's just taken an array of numbers and define a binary tree somehow. But why is that any good? The reason is that there's a connection between this and finding the range maximum. And so that connection is, if I have a range, I can find the nodes in the tree that correspond to the leftmost and rightmost entry in that range. I didn't comment on this earlier. In this tree, I've labeled every node with its in-order rank, or with its position from left to right. So we have 0, 1, 2, 3, 4, 5, 6, 7. So I'm just sliding a line left to right over this picture and assigning consecutive numbers. This happens to be the same as the index of the array element that the pole represents. So if I want the range from 6 to 14, I just find the nodes labeled 6 and 14 in my picture. Now, the range maximum always is the lowest common ancestor of those two nodes in the tree. And why is that? Well, from each of these nodes, we have to have a path to the overall maximum. If the overall maximum is within that range, then it surely is the maximum in the range. The other option is it's outside of the range. But then, because this is a binary tree, there must be some node where we split the path, where one part of the path continues to go to 6 and the other continues to go to 14. So there must be some node in the range between those two where the paths split. And that node, when that was generated, it was to the left or to the right of the overall root, or recursively, it was between two large things that are outside of the range. And then this was the first element in the range that was assigned a node. Or the other way to say it, the paths of these two nodes, they split at the earliest thing that is, well, they split at the highest pole that's between those two, because afterwards they will never be in the same subproblem. So if you have this range at any point in time contained in a larger range, for example, this one, then either 6 and 14 stay on the same side of the large pole, or they're separated now and for good. So that connection is a acute observation, and it goes a little further. So you don't actually need the poles anymore. All you need is the mapping from the array indices to these nodes. So you can find what are the nodes that correspond to the leftmost, rightmost position. And then you can find the lowest common ancestor from those. And that even works if you rearrange the y-coordinate of the nodes. In this case, it was still reflecting the values in the array. But all we're doing is looking at the in-order index of a node and finding lowest common ancestors. None of that uses the y-coordinate. So it also works if you just draw the tree in a standard way here, like the y-coordinate is just the depth in the tree. So all that's needed to answer range minimum queries is this binary tree. We don't need any values in the array. Let's see if that is clear enough. So here's a little Cartesian tree, and I haven't shown you the array that could go along with it. And are we 1-based or 0-based? It's always 0-based, right? So there's several steps now. Maybe one good in-between thing would be, how do I get these numbers? Here I still have them. How do I get, if I just have the tree as the usual pointer structure and so on, how do I get these numbers inside the nodes? I can do that with an in-order traversal, which looks as follows. I start at the root, and then at each node, I first process the left subtree, then I assign the value of the root of the current node, and then I process, the other way around, process the right subtree. First left, then myself, then right. That's in-order traversal. So, well, say left, self, right. And what does self mean? Self means I'm assigning myself the next free number. Let's do this on here. So I walk from the root. I first go left. Okay. I arrive at a new node. I first go left. Okay. First go left, first go left. Blah, blah, blah. I'll always walk down left, doing nothing. Now, at this point, there's no left. So I come back from the empty left, and now I assign the first number to this node. Okay? So this gets the 0, because I'm in the self part of treating this node. Then I go to the right subtree, that's empty too, so nothing happens. And then I return, and now I walk back up. Now I've done, for that node, I've done the entire left subtree. So now is this guy's turn, and it gets the number 1. I'm done with the self part of that node, so I go down to the right subtree. That again, I go to the left, empty, come back. Now I assign the next free number, which is 2. And so on and so forth. So here, right is again empty, so I come back. Right is done, so I'm finished here. Now I come back for this node, all the left subtree has been dealt with. So now it's the self part, so I'm assigning this node the next free number, 3. Now I go to the right subtree, but that's empty, so I come back immediately, go back up. I've done with the whole left subtree of that node, so guess what's coming next? It gets its number, which is 4. Now I'm going to the right subtree. Okay, I arrive at a new node again. First thing we do is go left. So we go left. There's no left here, so that one is treated next. It gets the next free number, number 5. Okay, so you keep going like this. If we do the same in this picture, walk down, the dashed line. Walk down, walk down, walk down until you can no longer. Then you return from the left. So this guy gets the first index 0. Nothing in the right, so we come back up to this. Let me finish drawing this path around the tree, and then we'll just follow it. So we're at this point. We're done with the left subtree, so this gets assigned a number. We go to the right subtree. There's nothing on the left. Now it's the self part, 2. Nothing on the right, so we come back up. This has all the left dealt with, so the next is assigned a 3. Then we go to the right. And if you keep assigning the indices with this, you get these labels for the nodes. So that also means you can project this down to the array entries. So there's 0, 1, 2, 3, 4, 5, 6, 7. Okay. What do we get for RMQ15 in this case? That's maybe the point where we can show the answers. There's various votes for various numbers. And first step we have to do is we find 1 and 5 in the array. That's the range that we're looking at. The trouble is we don't have the numbers in the array, so we cannot just use that information. Instead, we have to use the tree. So we go to the nodes that have 1 and 5. And we find the lowest common ancestor, which is 3. That's where they split. And so 3 is the answer, because at position 3, there must have been the maximum here. Okay? So this is the maximum if that's the Cartesian tree, even without knowing what the real numbers are. And here's one concrete, I generated the example using these numbers. There's others that would have given the same tree. If you look at the range 1, 5, then 7 is the largest here. And you can double check that you get the tree if you apply the construction from before with the poles and letting lines sink down. So there's that in nice again. Okay, that was step 1. That's the Cartesian tree. All this means so far is if I have the tree, I know for all the RMQ queries, I know what the answer is. It's not necessarily fast to find it, because I would still need to find lowest common ancestors. And now we're running a little bit in circles. In Unit 8, I told you, you can do longest common extensions by doing lowest common ancestors in the suffix tree. But now you see you need lowest common ancestors to do RMQ. So it doesn't seem to go anywhere. But bear with me for a bit. I use a larger example if you just generate some random numbers. But it's just a binary tree, really. The second important ingredient is the following. We can count how many different binary trees there are, and we'll find that indeed many different arrays will lead to the same Cartesian tree. So if you just have your RMQ classes on, all from an array that everything you see from an array are the answers it gives to RMQ queries, then many arrays are equivalent. They give the same answers to all RMQ queries. Because there's not enough Cartesian trees to give different answers. And given the Cartesian tree, all RMQ answers are predetermined, because all that you ever do is find lowest common ancestors. Okay. So let's first count the number of binary trees. If I have an array of length n, I'll have n nodes in this tree. How many different binary tree shapes are there? Well, you can look at small numbers. For example, for 2 nodes, a binary tree can look like this, or it can look like this. That's the only 2 options. How many do we have with 3 nodes? Well, there's the balanced one where I have this cherry shape. And then there's various ways of unbalanced trees where it's essentially a straight line, but it can be straight in different directions. And so it's overall 5 different options. These are all possible options. There's no other options. So people have studied this, and it turns out you can precisely calculate how many trees you can get with n numbers. That's the Catalan numbers. But this is not a combinatorics class, so I won't go into this at all. What's easy to see is an upper bound. And that comes back to the compression unit. What we can do is we can encode every binary tree with a certain number of bits. And because there's only so and so many bit strings with a certain number of bits, we get an upper bound for the number of different trees that there can be. Because the encoding will be such that I can reconstruct the tree from it. So more precisely, we can encode a tree with 2n bits. And then 2 to the 2n is the number of different bit strings of length 2n. And each of those gives at most one tree. So there's at most so many different binary trees. And what does the encoding look like? It's actually very simple. You do a traversal of your tree, similar as before. So we do this kind of walk around the tree. And whenever I visit a node first, I store whether it has a left and whether it has a right child with 2 bits. All right, so I'm using 2 bits per node. So for each node, I store whether it has a left and a right child, but just using 1 bit each. So this node would be, and I'm following this, so this node would be 1, 1, because it has both a left and a right child. This next node would be another 1, 1, because it has both children, and this one 2. But this one would be a 0, 0, because it's a leaf. And this one's also a 0, 0. And then this one is more interesting. It has no left child, so 0, but a right child, 0, 1. That's a 0, 0 again, and the 0, 0. And I would encode these in the order I find them following the orange line. So it would be 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. The question now becomes, how can I decode the tree again? That sounds tricky, but it's always possible. And stay where you are. To convince you, let me go to a new page, and you can rely on my poor memory that I can't memorize what the tree looks like, and I won't cheat. So you start at the beginning. You have 2 bits, and they say there's a root, and it has both children, because it's 1, 1. That means the orange line continues to the left. And there's another node, okay, also has both children. So the orange line continues further here. Again, we have 1, 1, so I'm here now. Now I'm seeing 2 zeros. So the next thing I'm doing has no children. It's a leaf. But then the orange line knows this is the next one we decode. That's another 0, 0, so there's no children. Then the orange line continues back up here to the next dangling edge. And that's a 0, 1. So it's a node with no edge here, but an edge here. That means orange line continues down here. And the last 2 things is, again, append 2 more leaves. Okay? And so if you check, that's essentially the same tree. It's just drawn slightly deformed, but the same parent-child relations. So we can encode a binary tree with 2n bits. Amazing. But how does that help us? Okay, I'll skip this one because we're otherwise running a bit out of time. is also not so important that you know the exact encoding. All we need is we can use 2n bits to encode any binary tree of n nodes. In the last subsection, we'll put these things together and use this fact that there's not too many binary trees and a short encoding for those to use the simple solution we've seen before with n log n preprocessing time on a slightly smaller instance. And then for the remaining bits, we'll have to use a new technique that you haven't seen so far called exhaustive tabulation. Just as a historic note, the technique is also known in the literature as the 4 Russians trick, which is a terrible othering term. So I'm refusing to use it. But you've seen it. If you see it in the literature, you should know what it's meant. So it's the same thing. Exhaustive tabulation is the 4 Russians trick. And, well, I mean, yeah, they were in the Soviet Union, not even clear if they were Russian. It's just a terrible name. So, but it's in widespread use, so you should be able to make the connection. One step is we already know an n log n solution. That's the sparse tables. And as I said before, it's enough if we can reduce the input size by a log n factor. If we can get the number of elements down to n divided log n, then the preprocessing time would be linear overall. So what we'll do is we'll use a blocking trick similar to some things we've done before. So we take our overall array and we use a judiciously chosen block size. Don't worry about the constants so much, but it's roughly log n numbers. And we treat those as a block. Now, what do we do with those blocks? From each block, we take the smallest element, the minimum in the block, and take that out as an element in this array B, which only contains the block minima. Now, if you look at the example here, I think it's to scale, but if you imagine the array gets much, much bigger, then this blue part is substantially larger than one block. This has roughly size n divided log n, because that's the number of blocks if I have roughly log n in each block, whereas the blocks are fairly small. So this B will be what we feed into our old algorithm with the n log n preprocessing time. So that we'll use here as our input of size m. So we use the sparse tables for this one. And what that means is with just using sparse tables as a black box, we can answer RMQ queries on the blue part, on the blue array alone in constant time. And we use linear time preprocessing, just because we've shrunk it just enough to be able to do that. Now, how does this help to answer queries? In particular, one easy observation, if I have a query that's just covering blocks entirely, then I could just translate that as answering the same query down here. And whatever is the answer is the overall minimum. That's fine. But in general, we will not have queries that are aligned with block boundaries. In general, we'll have something like this, a query that spans certain blocks entirely and then has an endpoint and start point somewhere in the middle of some other blocks. Well, we can still do some parts. So there's some range where it's entire blocks, and then there's at most one block at the outermost ends where we have to look inside blocks. And we'll use that to decompose our arrangement query. Again, the overall argument is the minimum in the entire query range is one of those entries. So it can be what's the minimum in the blue part, or it can be the minimum of that green part, or the minimum of that green part. That's 3 candidates. And I can find which one is the ultimate minimum by just comparing those 3. That's the idea. That's how we get to constant time queries. But we still have to work out how to find the minima in these other parts. What's spelled out here is just the formal way to say the minimum from this, the minimum from this, the minimum from these blue parts. It's a bit a pain because the indices need to be shifted around. So I want this to be block local, whereas this is global. And so if you read it in detail, it just works out to be the overall index of the minimum. So we have only 3 possible values left to check if we can find the minima in the blue and 2 green blocks. And the blue block, as I just said before, is already done. All we need to do is find a range minimum in this smaller array. And for that, we can use our previous data structure, the sparse tables. What's left is the intra-block queries, where I'm just concerned about finding the range min in this tiny range within one block. Okay. We want linear preprocessing time overall. And we have to do a preprocessing step for all the n over log n blocks. So we really can't spend much time on each of them. And we also want constant query time. So we have quite a lot of blocks, but they're all super short. And in particular, the number of elements in a block is chosen so that with our encoding from before, we get a small number. So what does that mean? Each of these little blocks, for the intra-block queries, we only need to know the relative order within the block. So all we need to know for RMQ queries is this little Cartesian tree within the block. And such a Cartesian tree with 2b elements, we can encode with 2b bits. That was what we've done in the previous section. But 2b bits here, that's just 1/2 log n, because b is log n divided by 4. So the number of different Cartesian trees of that small size is at most 2 to the 2b, and that works out to be square root n. So the number of blocks is large, because that's that number. But the number of different blocks from the RMQ classes perspective is not that large. It's much, much smaller. Square root is much smaller than n divided log n. So we have many blocks that behave identical to all RMQ queries we can possibly ask. And so that's where this new trick comes in. Instead of trying to store for each block individually how to solve queries, we store once and for all possible shapes of the blocks, how they solve the queries. So we have something of the order of n squared different possible small problems, and we just write them all down. That's why it's called exhaustive tabulation. I don't know if my actual problem uses all of these problem types, but I don't care because it's not so many overall. So I'll just write them all down. What this looks like is one large lookup table. For example, we could have this little, if that was our tree, so if b was 4, I have 4 numbers in my block. That's one possible Cartesian tree. It has an encoding of 1, 1, and then 0, 0, 0, 1, 0, 0. So the block type here would be just that encoding. And you can treat that as a binary number and use it as an index in an array if you want. And then I have this entry a few times for all possible RMQ queries. For example, from 0 to 3, that one has 0, that's 3. The answer must be 1 because that's the lowest common ancestor. So I have one row in this giant table that looks like this. I have another row with the same block type and say from from 1 to 3. That's for this range, and the answer is also 1. Then I have 2, 3. Here the answer is 2 because that's the higher up in the tree, and so on. So you just have one row for each possible block type and possible I and j within the block. But this overall table is still not very large because the number of block types is square root n. The number of combinations for I and j is b squared, but that's log squared at most. So the overall number of rows is still fairly moderate, much, much smaller than n. And we can generate the table in linear time, and it uses much less than linear space. So to put it all together then, you can use that to answer the intra-block queries in constant time by storing for each block its type. So you can use that, look up the right row in your large table and look up the answer for the intra-block queries. And then with finding the minimum of the 3 candidates, you find the overall minimum. And so that in total gives you a linear preprocessing time and constant query time solution for the range min query problem. And from the discussion from the beginning of today, that gives you also a solution for longest common extensions in strings. Now, if you think about the problem just as it is, you can't really improve either of those two. Constant query time is, of course, best possible. You at least need to produce the output. And if you want constant query time, someone at some point has to read the array at least once. So the linear preprocessing time is also best possible. The solution surely is a bit complicated. Maybe that's an understatement. I don't know. If you've seen it a few times, it appears less and less mystical. But it's a combination of more techniques in one place than we've seen otherwise. Everything I told you today kind of came together for this final solution. And there's a few things that are still that you can still improve, and that's the space for the preprocessing. The time will remain linear, but you can try to improve on the space and reduce the constant factor in the space. That's something that I've worked on. But overall, that is the solution for range min queries, which closes the last black box from Unit 8 that we left open, and showed you a little bit of more advanced data structuring techniques, especially this bootstrapping from an exhaustive tabulation technique is something that often allows you to reduce the space by some logarithmic factor. And so that's what's used in modern solutions for text indexing. They're based on what we've done in Unit 8, plus they further compress the size to handle the large data sets we have. That's all from Unit 9 and concludes all the material I have for you guys. We can go over the remaining questions, but it's just this one about the decomposition. Maybe we'll do that offline. What I would suggest for tomorrow is think of some questions. I still want to give you time to do the survey. We could run it now if you want to stick around. But maybe tomorrow is nicer, then everyone has a chance. And I'll send it on Campus Wire later as well. Send any questions you have on Slido to collect them. So we can go over some questions tomorrow, and we can do another round of this after the Christmas break. Depending on the demand or how much people are interested in discussing things, we can do more of those sessions. But you also have the tutorials. Okay, so let's do tomorrow as a normal slot. I'll send some instructions on what to do, and we can probably skip next week, unless you very much prefer talking about problems next week as opposed to after Christmas.